Okay. So first things is that I'll remind you that Monday will be test 2. Test 2 covers the material of units 5 through 8. So that's labs 5 through 8 and homework 5 through 8. So there'll be at least one question on the book from the chapters 5 through 8. And then the material on the test is labs 5, 6, 7, and 8 with all their parts. We'll be back in the classroom, I hope and think, by then. So those of you who want to come in and use the software here can do so. I will try to minimize the use of the software for those of you who have to be at home and are using the remote version, which can be slow, but there will be some simulation stuff that is sort of a standard part of the course. Okay. Somebody trying to chat with me. No, that was just me bumping up there. Okay. So you are expecting question 1 on the test to be an RC circuit, more like the RC circuit on lab 7 than that you saw on lab 6. So you expect there to be resistors that you have to combine and capacitors that you have to combine, and that the resistors that are involved in the charging circuit will be different than the resistors in the discharging circuit. You will calculate equivalent resistances, equivalent capacitances. You'll calculate time constants. You'll give me units for all those things. And then the measurement will be, I expect to hand you the circuit built, and then for you to run the simulation and show me the oscilloscopes and show that you understand how to measure the time constant in the simulation. What else do you expect? You expect something with the adder or register circuits. I provided you, go back to modules. I posted down here these web page, to my mind, equivalents of some of the circuits, the adder subtractor, the adder with registers, the parallel loading register. And so you can either use the circuits you built for the labs. You must build those circuits for the lab to get credit for the lab. But you, on the test, to make sure I'm not making you use the software too much, if you have to do it remotely, you can use these web page versions. So you're expecting something along those lines of, here is, put this number and that number. So adder with registers, put this number in register A, that number in register B, and show the addition, or subtract, 7 minus 2 and get 5. The parallel loading register. So you have to understand, to operate these circuits, it's crucial that you understand the notion of edge triggering. You're expecting something with a floating point number. Here's some decimal number, put it into a floating point representation. A floating point representation, get it into a decimal representation, which might be scientific notation, because the purpose of floats is to have a lot of a range available, so that the number might be very big or very small. There'll be some like wordy questions where I'm looking for some of the vocabulary of, and the vocabulary, there's some vocabulary, there's a lot of vocabulary in memory. and there's a lot of vocabulary in semiconductors. So I'll ask you some question where I'll expect you to say band or doping, or does it increase or decrease the ability to conduct. So that will so you're expecting. Okay. So at this point, I ask, are there any questions? I'm looking for either see if anybody's chatting with me or anybody's going to speak up. All right, should I ask myself some questions? So let me look at the calendar. Oh, somebody did chat with me. Hold on, let me see. Can you explain doping? Yes. Okay. So you won't need to, I mean, if it'll just be sort of as a vocab word or something like that, but so you won't need to like write an essay on the effect of doping or anything like that. But let me get a periodic table. That's what I'm looking for. Okay, that's big enough, I guess. All right. So in an atom, this column in the periodic table sort of is sort of how many the column is related to how many things are in the outer shell. The outer shell has the most effect on your behavior because that's what the world has access to, what's on the outside. So on the inside, they don't see, it's your bundled up feelings, but what's on the outside is what they interact with, what they see. So, we are like in this, there are more semiconductors than just this, but we'll focus on silicon and germanium. So they have 4 things on the outside. And so you have this notion of energy levels that turn into energy bands. And I don't want to redo the whole lecture, but I will say the silicon and the germanium are such that when you are putting electrons into bands, you fill a band. So let me draw at least a little picture here. Because that's one thing I might do on a test is sort of, I might have words or I might have a picture and say, what is this arrow pointing to or something like that. Or okay, so we have this picture where the energy is going up, and then the energy forms this sort of band. So you used to have a bunch of levels, and then the levels get together and affect each other, and then they just sort of spread out into a band, and then you have another band. So the levels spread out into bands, and then between the bands is a gap. So that's a band, and that's a gap. And it's the nature of semiconductors such that when I come along and put in electrons into these different levels, it's the nature of a semiconductor that I just fill a band. So it's just full. In a semiconductor. Okay. Okay. So now the idea is of doping, and that's like silicon or germanium do that. They are semiconductors. But if you dope it, let's say I dope silicon with aluminum, then the aluminum is going to have, so I have mostly silicon, but a little bit of aluminum, and aluminum's relatively similar to silicon. It's near it in the periodic table, but it's in a different column. So it has fewer electrons on the outside. So the bands are mostly the same as what they were before, except now when you dope with aluminum, I'm going to come along, oops, I got rid of all my bands. I didn't want to do that. Is there an undo? No, all right. So I had all my, go back to my green, fill in my bands. Okay, but when I dope, I empty up. So let me draw them as what we call a hole. So when you dope, this is called P doping. You get some holes, some empty levels in what's called the conduction band. Nobody yelled at me. This picture is terrible. That's not the gap. What's wrong with you? This is the gap. The empty spot is the gap. This is another band, and this is the conduction band. And that's not the conduction band. Had too many days off. This is the valence band. Because that's where the last electrons are in that band. So we call it the valence band. And then this one up here is the conduction band. That's where you have to go if you want to conduct. Okay, so I need electrons up there if they're going to move in a semiconductor. When I p-dope, I'm adding material that has fewer electrons in the outer shells. So there's some empty slots, or we'll say holes. It's not full, it's got some holes. One of the analogies people give, I give you my analogy of classrooms. One analogy that people give, another analogy people give is like a parking lot, something like that. So the parking lot is like full, and then 2 cars pull out or something like that. So now there are some spaces, so you can have your cars move from one space to another. Before it was there was no room to move when all the spaces were taken. Now there's some space. So that's one thing. That's what p doping does. It's some fewer electrons. It gives you some holes in the valence band, and then it gives you some conduction because things can move in and out of those holes. The opposite is n doping, which you grab from the other side, and then you have extra electrons. Doesn't mean you're charged, because along with the extra electrons on the outside, there's a nucleus that has a bigger charge. So it's not charged, but there are more electrons to fill these levels. And so then you end up with with n doping, you end up with something up here in the conduction band. And those electrons at least are around, available to move. So whether you p dope or whether you n dope, you improve the ability to conduct. You improve the conductivity. And so that's doping. So you take, you had some pure semiconductor, you bring in some, a small percentage of atoms that are nearby and have a slightly different behavior, that are similar but slightly different. And they take away, they ease up your semiconducting property. Your semiconducting property was that you filled one band and had to jump the gap to get into the other band. Doping gave you a little bit of freedom, gave you either the p doping gives you a couple of empty spots in the valence band, or n doping puts a few of those extra electrons, if you will, into the conduction band. Either way, you improve the conductivity. So that is the idea of doping. So I could say, you know, what could be on the test? I could say, you know, I had some pure silicon and I added some aluminum. This is known as, and then you can fill in doping. Or I could say P doping increases or decreases the conductivity, and you choose whether it's increasing or decreasing. Or I could have a picture and say, you know, what am I pointing to here? I'm pointing to the valence band, or I'm pointing to the conduction band, or I'm pointing to the gap or something like that. So I can have a picture and I ask you to give me some words. I can have some multiple choice kind of a thing where you have to pick the choice. So something like that. Which one increases and which one decreases? They both increase. They both increase. The semiconductor is a good question. The semiconductor is right at the spot where this is full, where the valence band is full. So there's no room to move. And so if you try to make it move, you have to take some electron and move it over the gap and then into the conduction band. If you p doped, you make a little bit of freedom in the valence band and it improves things. If you n dope, you put some electrons up in the conduction band and those ones are free to move. Freedom to move is conductivity. So either way, you're improving the conductivity. So it's not this one improves it and it's not this one increases it and that one decreases it. It's that they both increase it. Then we do that crazy thing where we put a P next to an N, make a P-N junction. And that's that crazy thing where we made it better and then we make it worse. But we made it a worse conductor, but we made it a conductor that has a direction, that there's a what we call forward bias and backward bias. So a P-N junction is a diode and it has a direction. So when we take a picture of a diode, they look like this. And that arrow part of it is supposed to, so that's a diode, which is made by putting a P and an N next to each other. So that's a possible sort of vocab question of, you know, another name for a P-N junction is a diode. And then, so we had the semiconductor, it wasn't a good conductor. We P-doped it, we made it better. We N-doped it, we made it better. Then we put the P next to the N and we made it bad again. But we're not worried about it being a conductor. We're worried about it having things, if we wanted a good conductor, we just use a metal, you know. But what we want is this, with the diode is this directionality. It's also non-linear. The resistor, one of our previous elements, was linear. The current is proportional to the voltage. That's not the case with a diode. And so a diode has much more of an on-off property. So we're getting to the point where we have the logic. The whole course had this physical side and this logical side. And with semiconductors and diodes, and then the next thing we'll talk about is transistors, we finally got to the point where this physical thing and the logical stuff meet up, because linear stuff doesn't lend itself to logic. Linear stuff is the voltage is a little bit more and the current's a little bit more. We want stuff that's like on and off. I mean, all of a sudden, you know, you flip the switch and it's the behavior's not some kind of gradual increasing thing, but some sort of radically different behavior. And diodes and transistors have that behavior. So that was some good questions in terms of like vocab, like the in terms of semiconductor vocabulary. So we should understand the concept of band, of gap, of this idea of filling the band, this band being full, the upper band being empty, and then the doping, sort of changing that situation, making it a little bit better. So we make it better, then we make it worse, but the worse has a direction, and so we love it. And it also has a nonlinearity, which we also love, because that takes us towards logic. Anything else on this or other things? I have some questions to ask myself if you don't have questions, but I'd rather answer your questions. I'm just going to peek at the calendar. So here we are on the 7th, and the 12th is the test. And we've started Unit 9, but we haven't finished it. So if we talked all today on questions, which we could do, then we could finish 9. Then that week do some 10 and some 11. And then we have this week, and 12 is just one circuit. There's not a lecture, it's one circuit. I can post it up early and people can start doing it whenever. But so we have time. So you're not throwing me off a schedule if you have questions, and I'm going to ask myself some of things I've graded and see people keep getting wrong. But I want you to, I'd rather you ask them than me ask myself, but I will ask myself if you don't ask me. But I may not ask your question. So, any questions? I think I have volume, so you could actually speak if you want, but I will read your chat if you're more comfortable with that. Okay, well, let's do one thing while I'm talking about a diet. Let's look at one question in that lab on diodes that people were, let me open up that lab. And I don't, so that was 8. And I forget what part it was in. Maybe let's look at B. Okay, so here's this diode, and we're trying to understand its characteristics. What is a diode like? And one thing you've got to watch is that I asked for the, one thing is I have here, this is put no, make the battery 0, and you'll get nothing and you'll get nothing. And then here you're doing a division. Resistance is voltage over current. And so you should not, you should just like leave this blank. Let me do some save as. I don't think I enabled it. Okay. So this should just be left blank. because your math teacher told you not to divide by 0. So don't divide by 0. Now, the problem here for, I don't know, 3 or 4, I don't remember exactly, but for 3 or 4 of these rows, the reading that you'll get from the circuit won't be in milliamps. Okay, so this is not a number you're going to see. I'm only putting in 1/10 of a volt and somehow I got 0.6 of a volt. So this isn't, these numbers aren't, don't try to reproduce these numbers, you're not going to. But when you have low voltages, what you're going to see in terms of the current is probably a U for micro, a U which should be a mu, which stands for micro. But I ask for milliamp. So let's say it was 1.2, 1.3, I wrote UA, but I want it in milliamps, in MA. Then you owe me microamp is smaller than milliamp. So then you've got to move the decimal place three places. Oh, not 0013. So I moved the decimal place 1. It was here between the 1 and the 3, and I moved it 1, 2, 3 places to get to milliamp. So you don't have to show me this conversion, and you don't have to put the unit here in the row because it's up here in the header. So you could just say 0.0013. And again, I'm just making this number up. I don't know that it's this number, but I do know that there are the first couple of rows you need to convert. And so that's one thing that some people were doing wrong. They were forgetting to convert. Then don't forget a unit. Volts divided by milliamps is going to give us kiloohms. So we're going to have kiloohms. And this should be decreasing. It depends on your depends on what you do with your voltmeter. It may be flat and then decrease, or it may continually decrease. But it should be you shouldn't see it go up and then down. If it went up and then down, maybe you missed converting the current. But this does not have a consistent resistance. A resistor has a consistent resistance, but a diode does not. The resistance was quite high and then comes down. And that's sort of the nature of being on and off. It has it first of all puts up a very, even if you're trying to push it in the right direction. Nowhere here did we try to push it in the opposite direction, in the reverse bias direction. We're trying to put it in the forward bias direction, but even in the beginning, it kind of, I don't know, resists us a bit and has a very high resistance, and then it sort of breaks open. So again, that's that sort of like on-off behavior, then eventually will exploit and turn into logic. Okay, but that is an issue some people were having here. So pay attention to that. And I could put that sort of stuff on a test. I could get a different diode or change the circuit, change this resistor, or get a different, this is a particular diode, I could get a different diode. And I could give you, a little table of data and ask you to calculate some resistance. I'm not, it's not a hard thing to do, but it's an important thing to do to understand how different this is from a resistor. Okay. Now I had some people with this, okay. So this function generator, is another thing that some people either weren't doing or didn't know what I wanted or getting wrong. So that's just scribble, 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 and let me make new scribble, scribble, scribble. So the function generator gives you on the normal, when you set up, it gives you a sine wave. And so if you don't have the diode, if you just have the resistor, if you put in a sine wave to just a resistor and you look at the voltage of the resistor, you get out a sine. So you put in a sine wave, you get out a sine wave. And sine waves have positive parts and negative parts. If you include the diode, it does not like to move in the one direction. It doesn't like to move in the negative direction. It only likes to move in the positive direction. And then, so the positive doesn't matter. And then the negative gets sort of cut out. And then the positive, and then cut out. And then the positive. So it turns alternating current, AC, alternating current, positive and negative current, alternating, and the C is current, into, it's not, you wouldn't, this is DC. Usually when you say something's DC, you mean that it's, you know, completely constant. This isn't completely constant, but it is, in the strictest sense, DC, in that it only goes in the positive direction. So it's not a nice steady DC, but it is DC. So I'll put it in quotes, DC. So it's not what we normally mean by direct current, because that would then be flat and a nice constant voltage. This is not, but it is at least always positive. So it always has a given direction. It's not alternating. It's got one direction. And then if you do this crazy thing, then so that's called the full wave. So if you do the full wave, it's going to be positive and positive and positive and positive and positive. So it's still not flat, but it's closer. That's just me. I can't draw. Okay. So, you know, so it's not these, it's not like it's not that you're losing it so much as you're flipping it up. So you're getting more of what you put in, but in only one direction. So you're putting in this wave, this positive wave, and this negative wave, and you're getting only positive waves. But here you were sort of losing something. Here you're not losing it. You're flipping it. Okay. So that's what you should see in that section. And then let me just tell you the answer of what I want for this one part. Any questions? Am I missing any questions on this stuff? No. Okay. So, and now I'm just going to erase this. And I ask a question, what path does it take? So there's the positive and the negative part of the cycle. And I'm going to focus on the positive part of the cycle, this part of the cycle. And that means this is positive compared to this, because I'm in the positive part of the cycle. And so I start here. And then I have to end here. So what's my path? How do I start here, end here, and always go in the direction of the diodes? So I come in, I come here, I have this juncture here, and this guy says, don't go this way, but go that way. And then I come down to this junction, and this says, don't go this way, but go through the resistor. It's important you see that this is a dot, this is a connection, this is not a dot. That's not a connection. That's just two wires passing in the night. They don't talk to each other. This is a junction. Now, these diodes are both pointing in this direction, so I could go to either. But this would take me back to where I started, and that's not what I want. I want to go home. I want to get back to the other side. And so I take D3 and then go up. Okay. So I started here, ended here, and that's the positive part of the cycle. And the oscilloscope here is measuring the voltage of the resistor, and I'm going in this vertically downward direction. So it sees a positive voltage. All right. Now I'm going to do the other part of the cycle. All right, so I'm going to start again. I'm going to do the other part of the cycle. So now here's my cycle. And now I'm going to be in the negative part of the cycle. And that means that this is negative. I'm thinking of this is 0, and I'm in the negative part of the cycle. So that means the middle is more positive than this end. Even though it's marked with a plus, I'm in the negative part of the cycle. So the 0 is bigger than this negative number. So now I'm going to start here and end up here, because that's the part of the cycle I'm in. I'm in the negative part of the cycle. This is 0, this is negative. So I start at the relatively positive thing. 0 is relatively positive compared to a negative number. Okay, so again, that's not a dot there. So I come out of here and I come over here, again, not a dot. And then I come up here and I can't go that way. That's what diodes do. They give me a direction. I go this way through D4. I come up here. I can't go through D2. That's would be in the wrong direction. So I'm forced to go down through the resistor. I go through the resistor. I come up. That's just 2 wires passing in the night. There's not a connection. And now I could go through either D3 or D1, but D3 takes me back where I've already been. I don't want to do that. I want to go home, which is the end. So I want to go through D1. And that takes me home to D1. Through D1 up to the plus, which is where I'm ending this time. Okay. Now what you see is that I'm in the negative part of the cycle, but what am I measuring? I am measuring the voltage across the resistor. And once again, in the resistor, the current is going vertically down through the resistor. So once again, that's why this negative part ends up giving me a positive thing for the oscilloscope. The oscilloscope will see a positive because that's the direction seen by the resistor. So these diodes determine when I'm in the positive part of the cycle, one direction. So I'm always going through diodes. Before, when I only had one diode, I was sometimes going through it, sometimes not going through it. But with this arrangement, I'm always going through diodes. It just switches which diodes. Right now, I'm going through 4 and 1. Previously, I was going through 2 and 3. So I'm always going through diodes, but I am going through different diodes depending on my cycle. But I'm always going through the resistor in the same direction. So that's why it's always up, up, up. Okay. And some people, I think they just didn't know what I wanted by these paths, but this is what I want. No, I didn't take many points off of those people, only a nominal point to say, hey, you got it wrong. Please understand. But now the people who drag their feet get to have like a point or half a point higher than those people. But there we go. Questions? on this. Again, I'm just sort of asking myself questions of things that I saw people getting wrong. Will this path finding be on the test? Good question. Usually I don't do that. I will tend to, I might ask very simple, like yes, no question, like is the diode in like, here's one, not this like, changing situation of the function generator, but I could draw one circuit and say, is it conducting or not conducting? Sort of, is there enough voltage to get it, is the voltage pushing it in the right direction? That would be at least a possible question I might ask in terms of directions. That's an important property of diodes. But for us, a more important property is their use as logic, ultimately. And so that comes in with this, here's this table of voltages and currents, and see that it's not like resistor, see that it's nonlinear. So I won't ask anything this involved. I might have a simple circuit and say, is it, at this instant in time with this particular voltage, is it or is it not conducting? And it's usually a simple question of, is there a voltage? And usually there has to be not just a voltage, but sort of enough of a voltage. So is there like, 0.6 of a volt in the direction that the arrow allows it to go in, then you would say, yeah, it's conducting. So it won't be this involved. It'll be sort of a simple, like, here's one diode, is it or is it not conducting? So it'll be much, I might not ask it at all, or it might be simplified, or it may be vocabulary for you to understand the vocabulary of diodes. There is a forward bias and a reverse bias. So the direction in which it can conduct is known as the forward bias. The direction in which it does not is the reverse bias. So there's some vocabulary of it. If I'm doing anything in terms of paths, it will be a very simple, sort of almost yes, no question. And you always guess. So, if you have no idea, you say yes or no, and but always make a guess. Because I give you some half a point if you guess wrong, or if you don't guess, I say, well, you knew that you didn't know it, or you took a guess. So I always try to not give you 0. All right. Anything else? Again, there's the big question on that we're going to start off with RC circuits. And then there's also going to be floats, and you have to show me the floats. You have to show me some intermediate steps, so you're not going to get credit. I know there are calculators, but if you don't show me some intermediate steps, I'm going to not give you all the full credit. So. Are there any questions that you have, or am I going back to asking myself questions? Because I do have questions for myself. All right. So I will ask myself a floating point number. All right. So let me ask myself a floating point number question. So let me, people were struggling, I think the most, at least the people who've done their labs beforehand, I kept trying to get you to ask me, like today, I kept trying to get you to ask me questions. I kept trying to get you to ask me a question about the numbers whose magnitude is less than 1, but people weren't asking me anything. So let's make it a negative number, 0 point, a couple of zeros, and then some number, okay. So there's some number, and I want to take that number and make it into a float. Okay. So let's just do the simple thing. The sign bit is going to be a 1. Okay, it's a negative number. The sign bit is 1. Now we're done with the overall negative sign. So it's just that easy. So again, you're on the test, you're running out of time. I have some floating point numbers. I'm going to ask you, here's the sign bit, and here's the mantissa, and here's the exponent. And one part of it is simple as saying if it's the sign, if the number is negative, the sign bit is 1, or the other way around, if the sign bit is 1, the number is negative. So get that point or points. That's easy to do. Okay, so now I'm going to take the number. What number did I have? 000. And I'm working now on the mantissa, sort of the mantissa and the exponent at the same time. And we have 24 bits. When it comes time to store, it's going to be 23. But we pretend in the beginning that there's 24. So until we store, there's 24. Okay. And then there will be 23 or something like that, some rhyme to remind yourself. Okay. So I'm going to do this calculation. And came up as scientific. That's what I want. So point, oh, let me get the dot in there. Come on. Control copy, Control C. Okay. And then let's say Control V. Okay, so there's my number. And I'm going to multiply it by 2 raised to the 24. That gives me this. Control C. And then I'm going to take just the whole number. So I do a truncation, and then that, I'm going to go back to the calculator, but in programmer mode. Control V and paste it in there. And then here is my result in binary. And remember that we're playing around with 24, but we didn't get 24. It's grouped in these groups of 4. So that's 1, 2, 3 groups of 4. That's 12, 13, 14, 15. So it's giving me 15 bits. I wanted 24, so there are 9 missing. Okay, so I'm going to repeat this and get my 9 bits back. Okay, so now I'm going to take my number back to scientific. Multiply that by 2 raised to the parentheses. There's my 24 and the 9 I was missing. And here I have my number. And I'm going to truncate. Oops. And I'm going to go over to programmer and decimal. Oops. And there is my binary. Control V. Okay, there we are. And now I have the 24. 1, 2, 3, 4, 5, 6 groups of 24. And I'm ready to get the mantissa. And so I'm just going to remember that getting the mantissa, this first guy is the one that I don't store. So I have my mantissa, not this red one, but all of the other things there. Okay. And then what? Okay, so I had at this stage, let me come back here, and I'm thinking of this as dot 1, 2, 3, 4, 5, 6, 7, 8, 9. There are my 9 things that were missing. That's how I'm thinking of this number. And now I have to figure out the exponent, and I have to move, my rule is to get this dot after that 1. So I have to move it, those 9 and 1 more. And I'm making this number bigger, so my power of 2 is negative. So it's 2 to the minus 10. And then I have to do my, what I call biasing. So I take the minus 10 plus my bias of 127. And so here I'm in programmer mode, clear, decimal 127 minus 10, which is 117, I knew that. And that is here. Okay, there are 8 bits. It didn't show me the first one, but I know it's there. Okay, so that then is the answer. Here is the sign bit was a 1 because it was negative. The mantissa is this number without the 1, and the exponent is, so this was mantissa. And this is exponent. Come on. Okay, and then we can do the check. So it's float, and I use some guy named Schmidt. There he is. And what was my answer? My answer was that the sign bit was a 1. My exponent was 0, 1, 1, 1, 1, 1, 1, and then 0, 1, 0, 0, 1, 0, 1. Okay. And then what was my mantissa? I'm not going to use this red one. So it was 1, 2, 3, 4, 5, 6 zeros, and then a 1. 1, 2, 3, 4, 5, 6 zeros, and then a 1. And then 1, 2, 3, 4 zeros, and then 101. 1, 2, 3, 4 zeros, and then 101. And then 1, 1, 1, 0. 1, 1, 1, 0, and then 0, 1, 1, 0. And there's the number minus 0.000984. U2. All right. And so we're pretty close to that number. Okay. And the question is, why is the exponent minus 10? Okay. Well, the exponent's really 117 after I bias it. So, but why is the power of 2 minus 10? Okay. Okay, so my usual game is I'm looking for 24 bits. So when I have a whole number and a fraction, then I see how many bits are taken up by my whole number. And then I deal with a fraction with what's left over. But I had no whole number this time, so I'm playing the fraction game with all 24 bits. And I'm supposed to have 24 bits, but I didn't get 24 bits. I got 15 bits and I'm missing 9. Okay. So then I think of that number as that I have at this stage as it was less than 1. So there's the dot. And the 9 zeros are out front. So I was expecting, I have a fraction. I don't have any whole number. So it starts with the dot. I'm looking for a fraction that takes 24. I didn't get 24. So this game down here is to get me all 24. But this game up here tells me what my exponent is. And so it was dot, no whole number, so it starts with a dot. I was missing 9 things. So there are the 9 zeros I put. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then our scientific notation rule, if you remember the rule of scientific notation, there's always 1 digit and then the dot. And the floating point is the same rule. There's always 1 non-zero digit and then the dot. In binary, that 1 non-zero digit has got to be a 1. That's why we choose later on not to store it, because we know it's a 1. But to get that dot here, because that's our rule. Why do we get the dot there? Because that's our rule. We follow the rules of floating point notation, and that was the rule that was invented, and we must follow it. So that means I was missing 9, but to follow my rule and get the dot in the right place, I have to move it not only those 9, but 1 more. So that's the 10. This number and the exponent, after I bias it, I'll have the exponent. But I'm thinking of this number as times 2 to some power. When I move that dot, I am making this number bigger. And so I have to make the power of 2 smaller to compensate. I don't want to change the number. I just want to re-represent it following these rules. So when I move this dot, these 9 places and 1 more, when I move it 10 places, I've got to compensate that with a negative power of 10. And then their way, in these rules, their way of being able to deal with positive and negative powers. We see here in this example that we need the possibility for negative powers. But their way of dealing with it is this so-called thing biasing, where we add for a float, which has 8 bits for the exponent, our bias is 127. So we take our power of 2, which was minus 10, and then we bias it, giving us 117. We represented that binary, and that's what we got. When we have a whole number, if I did one of the whole number ones, then you would say, how many bits were there in the whole number? And let's say there were 7 bits in my whole number. And then you say, but how many places do I have to move the dot to follow my rule? It's 6. So there's always one different, whether you're dealing with a number that's a whole number or dealing with a number that has a fraction. There's always this with a number that's less than 1, you're sort of adding it because you got to get this dot here. In a whole number example, so just say number with whole number with a whole part. Let's say I said it was 7 bits, so 1 0 0 1 2, 2, that doesn't make sense. 1, 1, 0, 0. And then there's a dot. So I had 7 bits in my whole number. I'm just making something up. Imagine there were 7 bits in my whole number. Then if I have to move this to obey my rule, then it's 1 and then a dot. I have to move it 6. So there's always this difference in 1. When it is, when you're dealing with a number that's only a fractional part, then you say how many parts were missing, how many bits were missing, 9. And then the exponent is 10 and it's negative, and then you bias it. Down here, if you had a whole number and it took up 7 bits, then you would say, I have to move this dot 6 places. I'm making the number now smaller, so my power of 2 to compensate would be positive. And then I would, again, bias it. So I would take, in this number, I would take 6 plus the 127. So you're always either adding or subtracting. So you play some game to work towards getting your mantissa, but you're also working on getting your exponent. But you're always, it's always sort of this off by 1 thing. So in, again, the negative, the number with a magnitude of less than 1, you find out how many things are missing, and then you add 1 to it. There were 9 things missing, you make it 10, and remember that the number was small, so the 10 is negative. If the number, if we had a whole number part, then we say how many bits did we get? We got 7, but how many shifts are we going to do? We're going to do 6. And another thing too, some people had labs in which the check didn't check. You know, like on the test, that makes sense on the test. Okay, if I ask for the check, you give me a check, whether it really checks or not. But when you're doing the lab and you have the time and you do a check and it doesn't check, that's your cue to sort of say, what's going on here? I'm doing something wrong. So this, for us, this check did check out. But if I had gotten this wrong, if I did this 9, or if I did this, forgotten, made this positive or something like that, then this number would be a completely different number. And I would say, that's not what I'm supposed to get. You know, so this calculator is not supposed to just give you the answer. If you just put things into this calculator and get the answer and write things down, you'll get some partial credit, but you're not going to get anywhere near the full credit, because I want to see the parts and the reasoning. But if you, again, if you do it and it's wrong, that's what it's supposed to be, a check. So if you use it the way it's supposed to be used, and you did your work and then you did your check, that would tell you that it's not checking. There's something wrong with your approach. Any other questions? So this was the floating. People got the other ones. Some people got the other things wrong as well. This was the one that sort of most often wrong. So that's the one I chose to go over. But I could go over one of the other ones in the sort of 9 minutes remaining. I probably don't have enough time to go through an RC circuit, or if you have questions. So I could say I'm done. You could ask me to do one of the other floating points, or have other questions, or we could be done. It's up to you. I hear nothing. I see nothing. I see typing away. All right. I'm going to call it there. I'll stop recording. I'll take my attendance, and then I will hang out a little bit for questions. Though I do have another meeting. Stop recording.